Hi everyone, I am Dr. Peiris. Welcome to the classroom. Today I am going to show you NAND implementation. So in this lecture, first I'll discuss about the NAND gate and what are the importance of NAND gates, and then what are the equivalent logic symbols for NAND gate, then how to implement circuits using NAND gates. So a NAND gate is called as a universal gate because you can implement all other logic gates as well as logic circuits only using NAND gates. And these NAND gates are easier to fabricate with electronic components. Now let's see what is the NAND gate. So here is the gate symbol. So basically a AND gate is followed by an inversion. The bubble basically tells inversion. These are called compensating bubbles or the bubbles. So the AND follows the bubble, which means AND follows a NOT. So this output expression is written as AB, which correspond to AND. Because of there is a bubble, it is AB prime. So the bubbles basically tells that it's going to be a complement. So it's the AB complement. So basically what happened in a NAND gate, it's the AND and then it becomes the complement. So if you look at the truth table, it's the opposite of the AND truth table. So if both are 1 1, you get the logic 0, otherwise everything is logic 1. Now let's see what are the equivalent logic symbols for NAND gates. So here I show both 2 input NAND gates as well as 3 input NAND gates. So this is the general logic symbol for the 2 input NAND gate, and this is the equivalent logic symbol for the NAND gate, the equivalent logic symbol. So you see that looks like a O, but there are bubbles in the inputs. So which means what? If you give A and B, when it goes to the gate, it becomes A prime, B prime, and then it's O. So A prime or B prime. So following the De Morgan's theorem, if you have X prime or Y prime, it is basically XY complement, which means this one can be written as AB complement. So this is same as that. That means we can use either this symbol or this symbol to denote a NAND gate. So both are NAND gate symbols. Same thing for the 3 input NAND gate. This is a 3 input NAND gate. The output is ABC complement. Now once you have the inversions in the inputs of the OR gate, they are going to be A prime, B prime, C prime, goes through the OR gate, so it becomes A prime or B prime or C prime. And following this De Morgan's theorem, this equal to ABC complement. So anytime you can use either symbol. So this is very important when we're going to redraw the circuits to make the circuit works only with NAND gates. This is what we are going to use, and this one also. Now let's see how do we use these symbols to make the circuits only in NAND gates. So what are the steps to follow to implement the circuits using only NAND gates? So you must replace all the AND gates with NAND gates, and once you replace with the NAND gates, you basically introduce inversion or a bubble after the AND gate. So to compensate these inversions, you must put the bubbles at inputs of OR gates. So let's see what does this mean. So this is the circuit which I have. I need to convert that circuit, or I need to implement this circuit using only NAND gates. So what should I do? I'm going to follow these 2 steps. So the AND gates become NAND gates. Now let's draw that first. So I'm going to find the equivalent logic circuit only with NAND gates. So I'm going to make these 2 AND gates NAND gates. So which means I put a bubble here and my inputs remain same, WX here. Same thing I do for the second one. Inputs are Y and Z, and I make this a NAND gate. So these 2 AND gates became NAND gates. Now I need to go and combine them. Now what does it say next? Place compensating inversion bubbles at inputs of OR gates. So here is the OR gate. I need to put the compensating bubbles. So since I add the bubble here, I need to compensate that bubble. So I put the bubble over here. Basically you are doing the inversion there. Same thing here, you made an inversion. So to compensate that, we must put an inversion here and then do the OR gate. So it's the same OR gate, but you put the bubbles in here. And here is the output F. So if you remember, this is the other circuit symbol for the NAND. So all three are NAND gates. So this is not O. Once it has the bubbles in the inputs, it is a NAND gate. So all three are drawn using NAND gates, which means we implemented this circuit only using NAND gates. So this is what we do for all types of questions. Let's see another one. So this circuit must be implemented using NAND gates. We do the same thing. So first I replace this one with the NAND gate. So here is the NAND gate and my inputs remain same, X and Y. Now I'm going to go to the OR gate. So the OR gate, in the OR gate I need to put the inversion at inputs of the OR gate to make that a NAND gate. So this is a NAND gate. Now one important thing here, so this bubble is compensated using the bubble over here, but the bubble that we added on the bottom input is not compensated, which means to compensate that we need to take the complement of the variable. This is Z, so I'm going to make it Z prime. So which means we are not altering anything. So once the C prime goes through the bubble, it becomes Z. So it's the same thing, so nothing is inverted. So that is something important to remember. In this case, that inversion is already compensated with that inversion, but here this inversion does not compensate, so you must take the complement of the original input variable to do the compensation for this bubble that you add. That's how we do that. Let's do another one. So in this case we don't have the circuit diagram, we have given the Boolean function. So the first thing that we're going to do is draw this Boolean function using AND and OR gates. We drew the circuits with AND and OR. So whenever you have the complements, we assume that these complements are readily available, so we don't need to draw NOT gates. So let's just put the inputs and then going to draw with the AND and OR first. So first one is WXY, which is all AND. So I have WXY, that's the AND gate, that's the first term, and I need X prime Y, which is also AND. So X prime Y. So we do that assuming the complements are already available. And the last one is just the W, so you see that I have put the YY again, WW again. They are the same inputs, so rather than drawing the wires many times, you can simply do it like that. But it's the same W, it's the same input W, it's the same Y over here. So it's just a single Y, you need to take them down here. So just to make the circuit symbol, you can just rewrite those input variables without drawing the wires everywhere. Now we have these three. Now they need to be combined through OR gate. So this is going to be a 3 input OR gate, and here is the output F. So we combine the 3 terms using the OR gate. Now we have drawn everything using AND and OR. Now let's convert that into NAND. So again we're going to do the AND gates to NAND gates. So this becomes NAND, input variables WX, Y. Same thing I do for this second one. Change it to a NAND. Inputs are X prime, Y. Now I need to place compensating bubbles for the OR gate. So we do compensating bubbles for the OR gate, and here is the output. So again, as in the previous example, you made the compensating bubble here, so you need to change it over here. So the W becomes W prime, which means you compensate that bubble over here. These are already compensated, so there is no problem with that. So make sure you do this one to make it correct. Let's do another one like that. So here, when we draw the basic circuit using AND and OR, so we start with parentheses XY OZ. So we first need XY. XY is going through an AND gate, and then it need to combine with Z. So XY and Z combine through OR gate. Here is the OR gate. Now that must be going with W through an AND gate. Here is W, so it should go through an AND gate. So the first term is done, and then we need XZ prime. XZ prime, it's an AND gate, and these two go with an OR gate. This is O. So this is the function. So this is using AND and OR. Now how do we change this to all NAND? All NAND. I am basically going to just draw on top of the same diagram because there is no much space. Let me change the colors to show you what happened with the bubbles. Now we're going to change the AND gates to NAND gates. So all the AND gates need to be NAND gates. So to make that, add the bubbles. So these change the AND gates to NAND gates. So this is already changed. Now we need to add the compensating bubbles for the OR gates. So here the compensating bubbles. Same thing here, compensating bubbles. Now what happened? So the top two compensate, but the bottom bubble, to make it compensate, we need to change the variable Z to C prime. Now this one is fine. Now these two compensate, this one and this one compensate, so everything is fine. So this is the old NAND implementation. So everything is in the NAND gates. So this is how we do the NAND implementation. So that's all for today, everyone. So I'll meet you again with another video. Please subscribe to my YouTube channel for more videos and for more lectures, and don't forget to visit my website drpeirisclassroom.com. You can find all the videos at one place. Thanks for watching, everyone. I'll meet you again with another video.